Okay. Thank you.
Yes. Yeah, I guess it's a good time to start. So this is my great pleasure to welcome Professor Andrea Lu. So Andrea Lu is a distinguished professor at the City University of New York, the founding director of the Photonics Initiative, City Advanced Science Research Center, and the Einstein Professor of Physics at the City University of New York Graduate Center. So he received his laurea, is it like a master degree and PhD from the University of Roma III, Italy. And after a postdoc at the University of Pennsylvania, he joined the faculty of the University of Texas at Austin, where he was the Temple Foundation endowed professor until 2018. So Dr. Lu is a fellow of many agencies like IEEE, IEEE, OSA, SPIE, American Physical Society, and others. And he also got a lot of awards, including Blavatnik National Award in Physics and Science Engineering, the IEEE Kyo Tomiyasu Award, the Vannevar Bush Faculty Fellowship, and the NSF Alan T. Waterman Award, among many, many others. So please welcome me, help me welcome Andrea.
Thank you, Alex. It's great to be here. Thank you everyone for coming. So today I wanted to tell you a bit about our research in the area of metamaterials and how we can use it to control light and sound. I will give a few examples of what metamaterials are, what they can do in the area of optics, radio frequencies, and acoustics. Sure it works. Is this the right controller? I can also use the keyboard. Unless
Yeah, it's off. On.
Okay, no. Okay, great. So to set the stage, motivate, I guess not everyone is working in this area. I want to stress how our devices, our technologies, especially in the context of electromagnetics, of optics, acoustics, the growing field of wireless, is very much limited by the set of materials we use. Typically, materials interact poorly with these waves, electromagnetic and acoustic waves, and therefore we typically need a large footprint, we need strong ways to enhance these interactions through resonances. In that context, metamaterials give us an interesting opportunity forward. Engineering at the nanoscale, materials at this sub-wavelength scale, can provide us with opportunities to create new forms of wave-matter interactions that are very much different than the constituent elements. So typically, we can start with a material set that is quite common, like silicon, glass, metals, but by engineering the shape, the alignment, the orientation, the composition of these nanostructures, we can create materials that can be treated as homogeneous in the bulk, but that have properties that are very different than the constituents and actually ideally suited for the application of interest. This can be applied to a wide range of different platforms, applications, devices, and functionalities. One interesting aspect that we've been pushing forward in the last few years has been the idea of actually playing with symmetries. Symmetries is playing a very important role in engineering these functionalities. You can see already in some of these structures how, for instance, we are playing here with the rotation between asymmetric nanoparticles, layer by layer, in constructing this material. This was for a broadband circular polarizer we did a few years ago. And this other structure has this T shape that has a broken symmetry in one plane to enhance second harmonic generation. This I don't have time to go through this application, but I will show you how symmetries can broadly control the way in which we engineer the material interactions. And to set the stage, I will show you an example of an extremely asymmetric response in optics and how we can use it to control light at the nanoscale in highly non-trivial ways. So to start with, I will talk about first a completely symmetric surface response. This is very similar if you are in a completely different area as hitting a pond with a droplet or a stone. You create these circular wavefronts. The same thing you can do with light by placing a very confined optical source, like a quantum emitter, for instance, very close to a homogeneous isotropic surface. You will get these optical wavefronts that go everywhere in all directions with the same wavefront. And if you engineer the surface right, you can actually largely couple this emitter with the surface and create strong light matter interactions at this point. The question is how to engineer these light matter interactions, how to enhance them, and also how to create strongly asymmetric responses. One way of doing that is to build a surface that actually has different asymmetric anisotropic responses. That can be done, for instance, by structuring the surface with a specific asymmetry. And this means these are the homogenized parameters of the surface conductivity along X and along Y, basically the response to electric fields polarized in orthogonal directions. If you assume that these are both positive or negative, this implies that the wavefronts will become elliptical rather than circular. But can you do more than that? Interestingly, if your surface has these conductivity tensor elements and an opposite sign, something very peculiar happens. First of all, what does it mean physically that these two elements have opposite sign of surface conductivity? It means that for electric fields polarized in one direction, the surface looks like a capacitive and a dielectric response. But for electric fields polarized orthogonal to it, the surface looks metallic, looks inductive in electrical engineering terms. We can do that by engineering the surface with extreme asymmetries, and I will show you some examples in a moment. But interestingly, what happens in that case is that the coupling of optical emission to that surface takes the form of this strangely shaped field. And if you take the spatial Fourier transform of this, you get these hyperbolic wavefronts in the plane. This is at fixed frequencies called an isofrequency contour. You're looking at the momentum as the reciprocal of the spatial coordinates. So this is kx and ky, the momentum along x and y. It takes this hyperbolic shape. Very different from the circular shape that you would get by Fourier transforming an isotropic response or elliptical. The difference between these two curves are not just the shape, but it's actually its topology. One is a closed contour, this one is an open contour. And the difference implies a drastically different light-matter interaction coupling. In fact, you can prove that the metric to quantify the interactions of light with a small emitter is determined by the fixed frequency, is determined by the integral over all momentums of light. And of course, an open contour gives you more integral, effectively unlimited, if you have an ideal extremely anisotropic surface. So this implies that I can build extremely tight interactions of a surface with a localized emitter. It could be a quantum emitter, could be a classical emitter, and I can realize this over very broadband responses. This applies for all frequencies for which this condition is satisfied. A particular interesting condition, by the way, arises when you find that the transition between these two. So as you scan frequency, of course, these parameters will change following, if you are an electrical engineer, following Foster's reactance theorem or following Kramer's chronic gradations. And there will be a frequency for which actually the response hits the transition between these two. This is called the topological transition because you are changing the topology of these curves. And that transition must happen with something singular. When you change the topology of a response, it has to go through a drastic phase change. That's a singular transition. In this case, as you see, the light becomes canalized, confined along specific channels, despite the fact that the surface is actually homogeneous, and the response becomes the largest, because one of these two elements is crossing zero. So here, light-matter interactions are enhanced at the maximum level. So can we build this? This actually is a demonstration. By the way, historically, we started working on this. We proposed theoretically this idea in 2015, and this was demonstrated soon after by the group of Kun Park at Harvard in using epitaxial silver structures with grooves. We did it later using boron nitride in collaboration with Ray and Hillenbrand. Boron nitride happens to support naturally a phonon resonance in the mid-infrared. And we exploited the phonon resonance with the nanostructuring of the boron nitride surface. These are elongated strips of boron nitride. Essentially, the combination of that phonon response and the structuring implies that electric fields parallel to the strips give you that inductive response. But electric fields orthogonal to the strips, because they fill the gaps, get a capacitive response. This gives you, indeed, these are nanoscale imaging and the Fourier transform, is hyperbolic bands and is a highly directional excitation when you put, for instance, a small emitter or a scatterer on the surface. And these are measurements showing the launching these phonon polaritons, as we call them. Polaritons is a way to describe this strong coupling between light and matter. Here, the oscillations of light traveling on the surface drag matter with them, drag that phonon vibrations that drive the inductive response of the boron nitride at the surface. And here you see specifically at the frequency for which you get this canalized response, this light dragging matter in a directional fashion. You also see how these vibrations actually decay quite fast on the surface, and that's because light-matter interactions are enhanced, and this is associated with the enhanced loss. I will show you in a moment how we got rid of that trade-off between strong light-matter interactions and loss in with a photonic engineering design. To do that, we exploited again symmetries. And this is, by the way, work that we did in collaboration with Professor Krasnok and also Professor Chu from University of Singapore. We started by exploring theoretically these nano strips, and then we actually realized this experimentally in another material platform. The idea is to exploit the large anisotropic response of the individual surfaces and then stack them and rotate, play with rotational symmetry breaking in this pair of surfaces. What can we expect from this? So these are isofrequency contours, again, that Fourier transform, it's momentum space plotting that gives you the hints at the topology of the excitation at fixed frequency, so for fixed properties on the individual surfaces, by changing the rotation angle between the two. Each surface individually has an hyperbolic response. And this response, you see it in the gray lines of these curves. But the coupling of the two with the rotation implies that the two hyperbolas cross at a certain point in momentum space. Where they cross, if they're closely coupled, the isofrequency contour has this hypothetic crossing. That's where the response of the two surfaces is the strongest, because the momentums are matching at that specific location in momentum space, and you get the colored curves here for different rotation angles. So you notice, for instance, at 90 degrees, when these strips are orthogonal to each other, you get these curves that have four hypothetic crossings, and at the center you get these closed contours, this elliptical response. So what's very interesting of this curve is that you started from two surfaces that isolated had hyperbolic responses, you bring them close together, and the photons coupled to matter support a closed contour. That's already interesting. But what's more interesting is that as you change the rotation angle, the number of crossings changes. In fact, if you look at the 30-degree rotation angle, the two curves actually cross only twice. And as a result, because of simple topological considerations, the avoided crossing keeps the topology open. This you can predict with the back of the envelope calculation, considering the opening angle of the hyperbolas and the rotation between the two, just looking at how many times they are expected to cross. In between, as you change the rotation angle, you see that there is a specific angle for which a topological transition occurs. You go from open to closed. At that point, something singular has to happen. Here, the bands become flat, and at that point, you expect to see the strongest light-matter interaction. But now, interestingly, you do not need to track the material resonance to go through that topological transition. You can do it by spinning, by twisting the two structures. And as you change the frequency, you actually change the open angle of these hyperbolas. So you get this transition, here frequency, here rotation angle, and at each of these points you have closed contours because there are only there are four avoided crossings, open contours because there are two, and in between you have this point at which the bands have to become flat because you are crossing the topological transition. This, by the way, if you are familiar with condensed matter physics, may remind you of this work on Moiré physics in twisted graphene bilayers. This, of course, it's a very different setup. This is for photons, but by exploiting the large asymmetry of these surfaces, we're able to translate from electronics to photonics this type of flat bands, and very interesting things happen with photons at that time. So, how can we prove this? Of course, one way is to take those boron nitride surfaces and stack them and twist. There are actually there is an easier way to do it, that is exploiting natural material, palladium trioxide, that has been shown quite recently to support this hyperbolic response in the plane of the surface naturally. How is that possible? The simple reason for why molybdenum trioxide supports the hyperbolic polaridon response is that the lattice symmetries of the material support phonon resonances similar to boron nitride, but that are very asymmetric in the plane. So you can imagine two different phonon vibrations at different frequencies, and they are sufficiently strong that in the frequency range in between the two, you expect to be inductive because one has already passed the resonance, and for the other polarization, still capacitive because you still have to hit the resonance of the other. So basically, molybdenum trioxide happens to do the job for us. We don't need to structure the material. It's so asymmetric already naturally that we can expect this hyperbolic response. So the trick now is to simply stack two of these on top of each other and rotate one with respect to the other. The optical axis plays the role of our strips effectively, and we can expect that there is a large range of frequencies and rotation angles for which you see this transition between hyperbolic and elliptical, this type of magic angle, borrowing the term from condensed matter physics, at which there is a topological transition, strong light matter interactions, and you can experience canalization. These are simulations showing how this actually should work. Fixed frequency, we change the rotation angle, and we observe drastically different excitations. These are the Fourier transform, also matched with analytical predictions based on the individual surfaces, what I showed before, indeed showing that the results match very well. And these are the experiments using the near-field nanoscale imaging through a SNOM. Basically, this is now quite established techniques that was pioneered by Dmitry Basov and Hillenbrand and others, in which we use a nanoscale tip that vibrates at the low frequency, and by shining light on this tip and measuring the scattering, we can deduce that small scattering that comes from the coupling between the tip and the surface, and from that we can actually image these light polariton waves that travel along the surface. For a single surface, you can see these hyperbolic polaritons. For bilayers, you see that changing the rotation angle at fixed frequency, you can go from hyperbolic to canalization to elliptical. Same frequency, same materials, just switching twisting the angle between the two. And these are different samples in which we are tracking, by changing the frequency, the condition for which you get canalization, which you get this very confined light. It's quite impressive, right? You have completely homogeneous bilayers in which light chooses to flow just in one direction and drags matter with it. Actually, it relies on these highly asymmetric mechanical vibrations of the lattice of this material to drag light, creates basically a waveguide in the bilayer. And this is, I think, the most impressive result, in which we have a bilayer and we carved these nano slits, very elongated, very asymmetric, and we work at the canalization regime of the bilayer. So this central region is the bilayer. This is the calculated isofrequency contour. You see, they are very flat. So the group velocity, it should be orthogonal to these surfaces. That's where energy is supposed to go when you excite the surfaces. And you see they are completely parallel because the bands are flat. That means that the light can go only one direction. And here you see in experiments, independent of how the slits are oriented, you will always get the projection of that slit along the direction of propagation of light. So this is a way to do nanoscale imaging at the extreme subwavelength resolution, because light cannot diffract. Like the problem of conventional imaging is that typically light diffracts. As soon as it gets out of the source, it must expand. That's what we saw when we were looking at the stone hitting a point on a point. This is very different from what you get here. Right? Here, light is excited by these slits and has to go just in the direction, independent of the orientation of these slits. You see the projection. Very different from what you get in the monolayer here, in which here are some zoom-in version in which you just see the small sides of the slit that excite this hyperbolic And we proved long-range propagation and extreme sub-wavelength imaging in these samples. Now, my talk was promising to show you also what we can do with sound, and this is actually something we're quite excited about, mimicking these responses in metamaterials. So we have relied on what nature offers us, molybdenum oxide in this case, but of course that is fixed frequency because that depends on the phonon vibrations of the lattice of this material. It depends on the scale of these molecules. But in acoustics, we can build metamaterials. These are actually based on the Lego blocks. And here we did the same thing. We actually interleaved the two lattices with different resonances. And by choosing the angle, this interleaved pattern changes. This is really Moiré pattern. And you see how we predict this very different like droplet hitting a pond, going from hyperbolic to canalization to, elliptical to canalization to hyperbolic by just changing that rotation angle at fixed frequencies. And actually, we built this. These are different surfaces with different angles. These are actually pictures of the surfaces. They're just Lego blocks, two different sets. So they basically have a different resonance frequency, and the colors correspond to the two frequencies. By simply changing the arrangements, you can actually measure. These are measurements taken with a laser vibrometer. So we use light actually to measure vibrations of the waves on the surfaces, and from that we can actually see that propagation of electrodynamic waves on the plates. Can we do more than that? Actually, this discovery led us to look into other material platforms that naturally provide even more asymmetric responses. The first example was this calcite work, in which calcite works very similar to molybdenum trioxide, has that asymmetric response in the plane, but has one advantage. Molybdenum trioxide, you can just make interfaces in which the optical axes are asymmetric in the plane. Calcite, actually, you can cut it in different angles for which the plane in which the system is hyperbolic can be tilted with respect to the interface. And that gives you another degree of freedom, that angle. So instead of playing with two layers to twist the structure, we actually play with this angle here. So we don't even need two layers. You can think of a single interface in which you play with the angle between the hyperbolic plane and the interface with air. What resulted is some concept actually borrowed from quantum mechanics known as ghost waves. These are surface waves that had been predicted long ago, by the way, but have never been visualized or experimentally realized. And now we were able to demonstrate them in a polaritonic system, in a system in which light is dragging matter with it. So we exploit this large asymmetry that now is tilted in the plane, and what happens is that these are surface waves confined to the interface, but actually the phase fronts enter the material, enter the bulk as they propagate. So they have a complex wave number. We can actually predict it in simulations and experimentally visualize it. It leads to very interesting evolution as you change that angle. For instance, here you see at different angles how at the same frequency you can go from hyperbolic with different opening angles to actually elliptical. And these are measurements of the nanoscale imaging. As you change the orientation, essentially you have an hyperboloid, you are tilting, and the interface basically takes a sample of the hyperboloid. As long as the angle is below a certain angle, you still cut an hyperbolic phase front, but with different angles. At some point, you hit a critical angle for which the topology changes and becomes elliptical. Actually, the transition you also expect some canalization. And in fact, you can go even further. This is very recent work just published using gallium oxide. Gallium oxide has the advantage of having an extra asymmetric response. Basically, I told you how molybdenum trioxide or calcite have these two orthogonal resonances, that one is inductive, one capacitive in a certain frequency range. Gallium oxide has a similar property, but the two resonances are not orthogonal. Have actually a finite angle that is not 90 degrees and not zero. That angle creates shear. It's a mechanical effect. It's like having dragging one resonance as you couple to the other. So what this implies for the polaritons is something even more special. This is the response I just described, this calcite, monomer oxide. The hyperbolas are neat, we showed them, but they are fixed. The axes of the hyperbolas depend on the orientation of these two resonances. But if you now make them non-orthogonal, the response actually drifts with the frequency, because the two resonances are not anymore orthogonal to each other. So at each frequency, you expect still hyperbolic response, but this will shear as the frequency changes. These hyperboloids are actually drifting with the frequency. And we demonstrated this both with using a prism coupling. So here you see how hyperbolic responses are drifting with frequency, and also using the nanoscale imaging. We've also been able to show that this shear determines this highly asymmetric coupling. Basically, now light prefers to go on one of the branches and on the other. The losses are highly asymmetric because of this shear phenomena. This would not be possible in a symmetric, like uniaxial medium. You need to have this monoclinic response in which the two axes are actually non-orthogonal. Anyways, what I showed you so far is associated with guided waves. Right? These are waves guided at the interface. But we've also been very interested, especially for applications, to look at free space propagating waves. And again, using symmetries to interact in anomalous ways with waves, with light waves and radio waves that interact with surfaces. There has been a lot of interest in metasurfaces, in these patterned surfaces that can produce lenses, holograms, and other type of devices over a very thin surface. And some of you work on some phase arrays. These are similar principles and what we use in the microwave community for 10 years. Basically, structuring a surface to control the phase of the response as the wavefronts emerge from the surface. In optics, this field has flourished in the last 10 years or so. There are now companies selling meta lenses, basically flat lenses that can focus or pattern the wavefront of choice. These approaches to control phase at the nanoscale, patterning a surface, are very interesting, very powerful in terms of spatial control of light. But they have one defect, that you can design them very accurately for one frequency, but as you scan the frequency, you cannot really control how the dispersion of each element follows. Typically, this is required to be close to a resonance, and therefore they will change independently and make unwanted chromatic aberrations to the response. So here I sketched three different wavelengths that excite this surface, and you see how the pattern may be the one you want for one frequency, but the other frequencies, of course, may have some aberrations. The reason for this is that we tackle localized resonances at the subwavelength scale. So the spectral control is very poor, and the response is determined by this type of spatial patterning. In contrast, especially in optics, there is a wide range of work on non-local interactions, the most popular of which is gratings, resonant grating. If you have resonant grating, it's a periodic structure that supports a specific resonance for a specific frequency. Typically, linearly polarized wave hits the surface and gets reflected very efficiently, typically 100% reflection. The other wavelengths actually go through unperturbed. These are supported by very delocalized resonances along the surface. Each of these elements is poorly, weakly interacting with the structure, but the periodicity of the grading creates these delocalized points. So this type of grading responses are have a very good spectral control. You can make these very high Q features, but the spatial control, of course, is poor. You get just a response for a certain plane wave, certain angle, and a certain frequency, and you cannot really manipulate that pattern. Can you get both of these functionalities in surface. That's why we have introduced a couple of years ago the idea of a non-local metasurface that gives you full control over the quality factor, so the bandwidth of response, the polarization response, the coherence of the response, and the arbitrary polarization state on top of wavefront control. So you can imprint the pattern of choice to the metasurface. And this can be done selectively for specific wavelengths. So you can get both spatial and spectral control. I will give you a couple of examples of this response in a moment. So the way to do it, this is one of the ways you can do it, is to start from dark states, some resonant states that are, because of symmetry, completely dark. They do not radiate, they do not couple to free space. This is one unit cell of a periodic structure that supports a mode that, because of the symmetries of the modal profile, does not leak into radiation. So it cannot even be excited from free space because of reciprocity. However, on top of this, you can introduce defects that outcouple this response to free space. And the defects can be placed anywhere through nanostructuring around the unit cell, giving you control to the quality factor, the degree of disorder actually goes like the function of the perturbation to control the quality factor, and the position controls the polarization at will. In fact, in this theoretical paper, we introduced the possibility of getting these chiral quasi-bound states in the continuum. So we start from a bound state that is not coupling to free space. We open it up with this quasi in front by placing defects with the right strategy, and then by playing with the perturbation, we can couple in and out any arbitrary chirality, any arbitrary polarization of interest to the surface. This is an extreme example of this. This is a surface that, when excited with the left-handed polarization, it's completely transparent. So the surface does not engage at all with the input wave. But when you excite it with the right-handed light, it's transparent for most wavelengths. And for one wavelength, the line width of which the spectral bandwidth can be determined by the degree of defect of perturbation that you introduce, will engage the surface fully, reflect, but reflect at an angle. And the angle of choice is determined by the gradient of these rotations. So each of these elements can target the same frequency, the same polarization, but the rotation determines the tilt of the wave in reflection. And what can we do with this? We've been actually working with a couple of companies in realizing the thin transparent films that can aid augmented reality, essentially. You can see through at most wavelengths in the visible, but then we have these highly reflective responses for just a target circular polarization, and they all will focus an image into the eye by patterning the film. And this actually, if you do it for 3 wavelengths, as we've been doing, you get actually colored image that is superimposed to the background. It can be interesting for automotive applications or other augmented reality. Another thing we've been quite interested in pursuing is the idea of secure communications. So what does this mean? In a conventional grading, I was just describing you how you get this nice resonant response, full reflection for a specific frequency and a specific linear polarization. That's the typical response of a grading. Other plane waves, other angles at the same frequency do not engage the grading at all. So typically they fully transmit, right? And you may have a little bit of reflection that comes from specific parts of the wavefront that match the original plane wave. Can we generalize this to an arbitrary wavefront profile? Using the same principle, you can. In fact, this is an example of a highly tailored metasurface in which that is designed to engage a certain circular polarization. This can be arbitrary polarization profile with a certain wavefront shape. So when you send this pattern in, you fully engage the surface as you did for a plane wave in a regular gradient. And the result is that 100% of that energy gets reflected back as the time reversed version. You can prove that being an eigenstate of the system, the reflected response will be shaped the same way by time reversed. So actually, the polarization also is reversed. Any other wavefront, for instance, any plane wave, will engage very poorly. It's transparent. So you will hit the surface only with the right wavefront. So if you know what wavefront you should hit, you get a very strong response. Any other wavefront, any other polarization would actually be transmitted. This is an extreme example in which you excite the surface with a localized source placed at a certain distance, and you fully engage the surface, you get fully reflected, phase conjugated response. The outgoing wave that's diverging becomes a converging wave that goes back and reverse. If you move this source by location, you get a different wavefront on the surface. Actually, the surface is transparent. And you can see the beauty of this in this pattern, in which this is the input wave, the output profile of the reflected beam. The phase of the response is basically flat. So you are engaging the field as an eigenstate, as if it's a plane wave for that surface. Each pattern here adiabatically follows the response, and you can make it very selective. So this we call it a wavefront selective response. Another application of this that we are also very excited about is we're working actually quite extensively on these topics, is to realize thermal metasurfaces, we call them, or surfaces that exploit this non-local extended mode to tailor the thermal oscillations of a material. Typically, if you have a conventional, let's say that you have a black body, thermal emitter, that, as you know, emits broadly a broad range of wavelengths and or like unpolarized light with incoherent responses, you can transform that beam into something that you like, for instance, a certain polarization, a certain frequency range, a certain pattern, by adding a lot of optics around it. You can add a pinhole, a lens, filters to select the frequency, polarizers and wave plates to select the polarization. Here we wanted a circularly polarized beam, and a spatial light modulator to create a wavefront of interest. All of this, of course, comes at a price of footprint, but most importantly, of inefficiencies. Each of these stages is actually selecting out part of the emitted beam, and what you get out here is just a very small fraction of the thermal emission from the source. If you pattern the surface properly, you can actually engage the surface itself to thermally emit just that energy with that wavefront, with that polarization, and at that frequency of interest, with the coherence properties both in time and space as desired. And this all depends on these non-local oscillations that basically engage these thermal fluctuations. This could also be by the photoluminescence, but they provide coherence internally in the process. So this is an example of a pattern surface that emits circularly polarized orbital angular momentum of light as it gets out with a certain spin. Another application of these metasurfaces that we've been working recently with NASA is spectropolarimetry. So can we use this patterning and actually interleaving of metasurfaces to and exploit the non-locality of the surfaces to actually detect both polarization and spectrum of the input light? We can do this if we're able to efficiently couple opposite polarizations and exploit the diffraction laws of these quasi-periodic gradings. We use basically three interleaved metasurfaces. This looks similar to the Lego blocks I showed you, but now it's the nanoscale. So actually, the next slide, I think, shows you the interleaving of the three elements, each targeting specific polarization states and specific frequencies. These are the pictures of the nanostructured devices, and these are the responses that we got. Basically, on the vertical plane, we can detect all the polarization states of light. also the degree of coherence, and the horizontal axis, we can actually detect the spectrum. So we can see, for instance, these are two wavelengths the same sent at the same time, and you get with different polarization states, and you get the response measured on the horizontal axis. Another application of this non-local surface, these are all rooted into symmetries, right? We're controlling the symmetry perturbations on the surfaces to realize these unusual effects of the surfaces that are typically 100 nanometers or so. Another thing we've been pursuing in this context is the idea of analog computing, analog signal processing using metasurfaces. The original idea was actually now dated almost 10 years. This was just a conceptual paper in which we showed, together with Nadia Renghetta and Vincenzo Galdi in Italy, that we can design a multi-layered metamaterial in a way that as you send an arbitrary spatial profile of a wave to the surface, as the light emerges from the metamaterial, you can impart a mathematical operation to the impinging wave. For instance, in this case, a derivative. So arbitrary spatial wavefronts could be differentiated as they travel through the material, the speed of light with large efficiency without having to go digital. You can imagine how this can be important for many applications. In fact, we're particularly interested to apply this now in the radio frequency domain, in the context of reconfigurable intelligent surfaces, in which you can basically apply some of the computing operations you typically do by going digital, imprint them in the structure of the material. How does this work? We basically work again on the non-locality, on the momentum engineering of the image. Taking the derivative, for instance, is equivalent to do a filtering in momentum space. And this is commonly done, for instance, in Fourier optics, but this typically requires very large setups and inefficiencies. Here we can do it at the level of a single metasurface. Let me show you one example. We worked on these initial demonstrations with Albert Polman, and we showed, for instance, you can use this to do edge detection. This is a slit in which you transmit just the edges, because that's basically the derivative. And recently we were able to demonstrate this in this metasurface here for arbitrarily polarized two-dimensional objects, isotropic. So you have an arbitrary image, you let it through the device. This device can be placed anywhere. It's 100 nanometer thick silicon patterned surface. You can place it like a film in between the object and the detector anywhere. And you see through, you will see just the edges of that image. And actually, we discovered that mostly by chance in the experiment, that because this surface is isotropic but not dual polarized, that you can use this combined with polarization imaging. By adding a polarizer before the device, when you illuminate the image with a polarized light, you can actually highlight certain edges, certain orientations of the edges that are aligned with the polarization. This is because only PE light gets to interact with it. So you can actually enhance this. You can combine polarization imaging and signal processing in one surface. These are for slits. It's even more extreme. You can see that for polarizers along one side, you get these nice edges. For the other one, you get the other edges. We also did the dual polarized version in which this works independently. So depending on the application, you can do either one. I don't have it here. Another thing we've been very interested in is to use this type of surfaces to do analog computing, to solve complex mathematical problems rooted into the response. Basically, the idea that came up in this paper is to start from an arbitrarily posed integral differential equation and solve it by providing an input and looking for the output that solves this equation. The original proposal was based on taking one of these metamaterials and adding feedback, but what we realized is that resonant objects naturally have this form of feedback. So you don't actually need this large footprint. You can do it at the level of a very compact device. So this is one device we built in collaboration with Albert Polman. It's a metasurface. it's transversely invariant, but it's optimized in each unit cell in a way that when you interrogate it at different angles, you will get as output the solution of a complex integral differential equation. And more recently, we proposed that this was not demonstrated yet. We are now doing an experiment in acoustics. You can actually engineer a scatterer, a subwavelength scatterer, to that you interrogate from multiple angles. The scattering from this object will encode the solution of a complex integral differential equation within the scattering. So the speed of light, you get the response to a complex problem, input to output, by simply interrogating it and measuring the response to the system. So this is an optimized scatterer that solves this specific problem. You send an arbitrary input, and the output will be actually matches exactly the solution. And it's also, we proved, quite robust to disorder, I think, tell it here. But yes, also when you add the disorder to the system, you still expect to find the solution. These are superimposed the ideal solution of the problem and the measured one you get from the scattering. It's a look around the scattering. So the last part of my talk will deal with another type of symmetry. All of these are that I showed you so far are spatial symmetries that we break spatial symmetries and we encode in a complex object a non-trivial response. All of these, however, must obey time reversal symmetry. You can make an object as complicated as you like, but the wave equation still obeys time reversal symmetry. So you do expect that whatever you put in between two sources, you have if you have a solution that matches that connects A to B, you have an identical solution, just time reverse, that connects B to A. In fact, we exploit this in many of the applications I showed you, right? The bound state inherently is dark both for outgoing waves and for incoming waves because of this fundamental principle that is known in wave physics as reciprocity. So the transmission between A and B and B and A is, of course, a constant. Something that still people miss oftentimes is that the structure can be as complicated as you like. I showed you some very complicated designs, but as long as you only take spatial symmetries, you will always have to obey this type of response. Over the years, we have been looking at ways to break this response, and the way you do it is to apply a directional bias to the channel. The most common way, by the way, is to use magnetic bias. That's how our isolators and circulators in the labs work. They apply directional DC bias to magnet-optical materials, and you can get very asymmetric responses because of that bias that breaks time reversal symmetry. It's DC. We've been looking at ways to apply this bias without magnetic responses. For instance, you can move media, time variations in a material, or nonlinearities. All of these are ways to apply the bias. I will show you a couple of examples of this in the next few slides. The first implementation, this is now quite dated, was the first demonstration of a circulator for sound. How does this work? Basically, it's a hollow resonant cavity, symmetric. So we start from a completely symmetric response. It's a three-part device that you send light from one part and you distribute it evenly between the two. But then we add something that breaks time reversal symmetry, and this is airflow. By circulating air in this cavity, you can actually directionally route sound from port 1 to 2, isolating port 3. The directionality is imprinted not by geometry, but by spinning the airflow. And therefore, as you come in from port 2, light now, or sound in this case, will go to port 3, and from 3 back to port 1. What was quite impressive is that you can achieve this large isolation between ports in a symmetric device, compact device, by spinning air at a very slow speed, about hundreds of times slower than sound. And over the past few years, we've been interested in applying this to radio waves and to light. To do that, of course, there are various ways. the easiest way is to just map this one directly into an optical experiment. What's the downside? Is that light goes much faster than sound. So even if you have hundreds of times slower speeds, still working at like 500 times slower than light would be very complicated idea. In fact, people have done this, by the way. Inspired by this work, a couple of years ago, some group in China has shown that if you take one of the spin heads of a hard drive and you run it at kilohertz speeds, you couple it to a highly resonant optical device, you can achieve the same exact effect for light. And they showed isolation based on this frequency. We didn't go this route, and even earlier we have shown that you can do this in a, I would argue, smarter way by modulating structures in time. So let me show you how the system works. You start again from a symmetric resonator. This can be a micro ring resonator, can be a nanostructure, can be just a printed circuit. The trick is that you start again from a symmetric object. This supports degenerate resonances, left-handed and right-handed. Then you add a spatial patterning to the structure. If you choose the patterning to be roughly half a wavelength of the resonance, you split these resonances. This is very similar to the avoided crossing I showed you in one of the first slides. But you preserve the generality, and of course you preserve reciprocity. I told you, you can pattern as complicated as you like. You will still preserve reciprocity and time reversal symmetry if you do not do something to break the temporal symmetry. One way of breaking temporal symmetry is to modulate this in time. If you modulate with a pattern that is not symmetric, then you should be able to break symmetry. And we want to do it by spinning. So what do? We modulate different segments of this modulation in time with different phases. And this is what you get. So this ring looks like it's slowly rotating. Nothing is actually mechanically rotating. You are just modulating with different phases, the different structures. And the result looks like spinning. It's very similar to a Doppler shift, but it's exploiting the synthetic rotation that comes from mixing with another frequency, a low frequency. And the result is very similar to what we have in that ring for sound. And now you can do it with light. What's interesting of this setup is that you can spin very fast. In fact, you can spin at velocities faster than the velocity of light by just choosing the right phase. Right? Nothing forbids you to spin as fast as you want, because the speed is just the distance between the phases at different locations. And based on this, we've shown several devices, both for light and sound. In fact, these are 4-port circulators, 3-port circulators in photonic crystals, in micro ring resonators, different technologies. The effects at microwaves can be even more pronounced using integrated circuits, printed circuits. We can actually outperform most magnetic-based circulators based on these principles. They do not require magnetic platforms, so they're completely compatible with CMOS technologies. The only down price here compared to magnetic devices is the power handling, because these structures can become so much smaller than a wavelength that you cannot really pack hundreds of watts like in a large circulator. But of course, if you would use the same footprint, you would easily make it. In fact, one of the more interesting, from conceptual point of view, projects that we've been pursuing recently was the idea of using this for very high power applications in which you cannot afford to use a magnetic material. This is also a possibility. For instance, if you implement this in wavelengths. A related result that we were also quite interested about is using nonlinearities to break reciprocity. And in this case, what's actually quite interesting is that you do not even need the external modulation network to break reciprocity. You can actually exploit the signal itself as it enters and exits the device to bias the system. So you can build a system like this. This is a sketch. It's a 2-resonator system. Both are nonlinear resonators. There is a phase delay in between. This is the circuit implementation. And this system can be designed to be fully transmissive when you excite from bottom to top, but it can be fully reflective when you excite from top to bottom. So large asymmetry in transmission that is rooted in the fact that when you send a signal with the, of course, this has to rely on linearity, so there will be a threshold intensity. For too low signals, this is fully reciprocal, but there is a threshold intensity after which the response becomes something like this. It's a highly non-reciprocal response that comes from the combination of geometrical asymmetries and nonlinearities in the system. This is actually an implementation in a nanophotonic silicon chip. So it's just silicon patterns, but if you zoom in, you see that these are inverse designed resonators that control the asymmetry between the two. There is a phase delay, and when you send a laser, this is telecom wavelengths through this line, you get full transmission. Actually, insertion loss here it's about 0.5 dB. But when the signals come back from this side, do not go here, but actually reflected to a third part. And we've used this for a LiDAR automotive application to measure actually the distance from an obstacle. This can be done with large efficiency, can replace a magnetic circulator in a piece of silicon, essentially. Here we exploit actually the third order nonlinearity of silicon. Now, to bring this to the next level, you may argue that all the devices I showed you in this second part are all regular devices, right? So can we map them into metamaterials? Metamaterials are lattices of these devices, right? So what we did is to start from the individual elements. This you can think of the ring I showed you before, but now it's in an hexagonal lattice. And what we showed is that the symmetry breaking that comes from this spinning, synthetic spin of the individual elements can be used to realize the analog of a topological insulator for light or sound. Topological insulators, you may have heard the word topology comes back. It's a very hot topic in condensed matter physics again. Was the discovery that certain materials, thanks to the broken symmetry introduced by the electron spin with specific lattice configurations, can realize a material that is insulating in the bulk, but because of the topological features, it drives currents on the boundaries. And what we showed is that these synthetic spins that come from temporal modulations can actually engage in a similar way photons. So photons, of course, do not have an intrinsic spin like electrons, but you can endow them with these synthetic spins. And the results are very similar to what you would get in a topological insulator for electrons. You get a banger, so they're insulating, but then you can create an arbitrarily shaped boundary, and you can count on the fact, because of topological arguments, because again of geometry, that there must be a waveguide mode that travels around the boundary one way. This is time reversal symmetry is broken by this spin that highly robust. What is quite exciting of this result is that independent of the boundary, independent of the defects you may introduce, like this is a large defect you introduce at this point, or different truncations of the boundaries, there must be a mode that travels one way. It cannot reflect back because there is no backward wave yet, and it cannot scatter into the bulk. The bulk is insulated. So it can be inherently robust propagation of one-way photons in a system that can be acoustic, can be radio frequency, can be optical. This is the first demonstration that we did in elastodynamic waves. We used piezoelectric patches modulated in time with that same spin I showed you. Each of them is modulated with the same angular momentum, and that's the response again with the laser vibrometer. Shows this propagation along the boundaries. You can also do multiplexing here. You can route in specific regions domain walls, right? These are created by spinning with opposite momentum the two sides of these areas. So you can reconfigure the surface on the fly. And this is an implementation in an integrated circuit. So this is radio frequency. what we did is to build an array of 16 circulators, like the ones I showed you before. Each of them is spinning thanks to switches that are modulated with a phase. And this builds the most compact and most broadband photonic topological insulator ever built. We're very excited about this result. We do not use resonances here, so it's actually a continuous wave topological protection from DC to few gigahertz in a chip that is extremely subwaving. These are measurements demonstrating the inherent robustness of this response. Here we introduce the defects, and you see how the wave goes through. The defects find its way around. We can reconfigure it, as I said, with domain walls for multiplexing. And we demonstrated a couple of applications in MIMO configuration. This is a phase array in which we can reconfigure phase delays. This is true time phase delay, extremely broadband and robust to defects for scanning. I know some of you are interested in this type of problems. This is again another demonstration for beamforming for pulses, because we exploit the inherent broadband nature of these responses. And the last slide is on something that connects back to the beginning. I showed you a lot of polaritonics in the first part of my talk, and now I bring it back here. This is the first demonstration of a topological transfer. So transfer of topological order from photons to polaritons, to phonon vibrations. So what we did is to build one of these topological photonic crystals that write light. This is actually a domain wall that is routing light along this boundary. We put a boron nitride sample on top, and that is has a phonon vibration at the same frequency range in which the lattice supports these topological polaritons, and we do find this avoided crossing, this extra mode in which we can actually measure the degree of light and sound vibrations as we cross the momentum space, the band gap of this photonic crystal. So we are showing experimentally the transfer of topological order from the domain wall into the sound vibrations that are supported by the boron nitride. So this concludes my talk. A few opportunities to manipulate in extreme ways light, sound, a combination of the two in polaritons, using metamaterials, using either unusual materials or using common materials, but with nanostructuring can enable new opportunities for photonics, for acoustics, and for electrodynamics. Thank you.
Okay, Andrea, very interesting and a lot of information. So, do you have any questions, guys? Maybe yes.
One question. On one slide, you show computing, analog
Analog
computing. Can you go back?
Sure, yeah. I guess this was the first slide.
Yeah. So can you also implement quantum computing? It's not digital, so.
Yeah, that was my question also.
Oh, okay, with the same.
Excellent question.
Same approach.
Sure. I mean, we can go down in kind of intensities required up to few photons, and this is something we're looking at. We can implement algorithms, but we're not looking specifically in kind of replacing quantum computing architectures with this, or looking into qubits, for instance. But yeah, this we're not done yet. Our main application is really to replace digital, analog to digital to analog. We've been starting to work on this project a few years ago on a new topic. Actually, still active. I'm leading this team. We're in the 6th year, so it's almost over. Beyond in the no-cost extension phase. But in this topic was on atto-joule computing. So the idea behind it is not necessarily to go to quantum computing, but it's more into addressing the challenge in energy costs that conventional computing has at the moment. To give you an idea, when we wrote the proposal, this was 7 years ago, already over 10% of the energy used in the US is dissipated in data centers, right? It's a huge cost of every time you click on Google, there is somewhere in probably California in which some data center is actually spending a few hundreds of joules actually per Google search. Typically in the data center, the energy costs is 100 femtojoule per bit. So imagine how many bits we spend and how much that will impact our energy needs. So the goal of that MURI has been to push this down to the level of attojoule. And just to give you an idea of what an attojoule is, one photon is about 0.15 attojoules. So if we can do operations that are so efficient to bring it down to the few attojoule per bit, this would be a huge enhancement in efficiency for computing. And one of the two approaches, so one approach to address this problem is to go quantum. So really realize switches, modulators that can be triggered by few photons. That's one part of our MURI. We've been quite successful in demonstrating attojoule, I mean, typically tens of attojoule or 100 attojoule level per bit of devices. The other one has been really focusing on this approach in which we completely do it another paradigm. Instead of using switches, modulators, so go digital and then go analog again, we process some operations that are typically applied many times to different inputs, but basically embedding them in the design of our photonic circuit. And this allows massively parallel computing of large, in this case, large images. We can think of doing this for many operations, but also doing this in time domain. So to apply time domain operations to a signal, to manipulate the spectrum, for instance. And this would drastically reduce. If you do the calculations for very large inputs, massive data, this gives you not only a big advantage in terms of time, obviously, but also in terms of energy dissipation. So there is a connection also to the quantum aspects, but most of what we've been doing has been for this part of the project in the context of classical waves. Thank you.
Well, I was computing with this approach, what is the accuracy? What accuracy can you achieve?
Yeah, no, the accuracy is that's a great question, by the way. It's very good. We have shown, and this of course will depend also on your metrics and what the needs are. But for instance, this is an example in which we overlay what we can get from an ideal solution of a complex mathematical problem and the actual response that you get from the measuring the scattering around this single subwavelength element. For some applications, by the way, accuracy is not a big problem. In fact, for instance, one thing we've been pursuing quite extensively is this idea of edge detection or image recognition. We work actually with Denbury Technologies on some of these for satellite imaging, in which they're not necessarily very, it's not important that you get second digit accuracy on the edge detection, but if you can enhance the sensing and imaging for these devices, and you can do it in an energy efficient way, they are very happy to trade some level of accuracy for dropping the energy costs dramatically.
So this edge detector, what it does, basically it does the spatial derivative.
This one is for a second order spatial derivative.
Second order.
Second order for all angles, all polarizations. You can imprint them in a single surface.
And is it possible to do time?
Sure. In fact, we are working on this at the moment. In fact, this type of resonances are very good. As you know, they are as selective in the momentum space as in the temporal space. So you can actually do also derivative of pulses. So you have a pulse, and you would get, as you go through this system, you can get both edge detection and time derivative of the input with this design. But this is not limited to derivatives. You can do integrals, you can do convolution, Fourier transform, you can do many, as long as it's a linear operation. And we've just started a new rig actually on this topic, in which we are looking at adding nonlinearities to the problems. This, of course, it's a much more complicated problem, but we have some initial results that are promising. This is just started, by the way, last few months. But it does give you engaging strong nonlinearities, as I showed you, these large light matter interactions. You can introduce in the problem also nonlinear processing that essentially, of course, opens a lot more doors in terms of what needs there are today in processing.
For example, in quantum, so if we suppose this structure works with the wave function, which is the probability of finding in space a particle, for example, in space, the special derivative, meaning the moment operator. So after this structure, so basically this structure will convert the wave function into the distribution over the momentum. Yeah,
Absolutely.
and maybe
When you go to few photons, that's exactly what happens. This becomes a probabilistic. Instead of, in this case, these are measurements, but this will become probabilistic problem. And we've been looking at this.
and if integrated with the time derivative, maybe even solving Schrödinger equations.
Sure.
Such a system. Yeah.
Absolutely. And the beauty is that it's the same devices. It's just a matter of adding single photon sources and detectors to the system, but the devices are already there.
We have
Yes.
questions in the chat.
Yeah, in the chat.
Yeah, I think there are a couple more. Yeah. But I will look at the chat as well. Yeah, go ahead.
All these experiments are happening in room temperature, or what are the temperature ranges of the materials?
Everything I showed today is room temperature,
Okay.
but we do have also a system, cryo system, in which we are doing experiments, quantum experiments. Mostly, we're looking at materials like transition material cogenites, and essentially, when it's important to get down, we can go down to 1 Kelvin. And we've been doing a few of these excitonic polaritons, if you're familiar. I didn't have time to show you here, but yes, especially as you go quantum, the coherence that you can find at room temperature is important too. So we have a system that can do similar measurements, angular spectrometry, polarimetry for cryo measurements.
And
That's a
the
good.
second question is related to quantum transition. The entanglement, quantum entanglement is possible with this waves.
Yeah, we're looking at this too. We're in very preliminary stages, but yes, we're looking at quantum metasurfaces. Yes. So the question is, most of what we've been doing so far is just in the quantum arena is to show few photon responses, but we're looking at unique ways to exploit. For instance, to give you an example, this is completely unpublished and stuff we've been discussing actually this week with some of the group members, is the devices I was showing you for the nonlinear interactions. In fact, Alex has worked on this as well quite extensively. We have a paper that came out a few months ago on advanced quantum technologies, in which we showed that you can do quantum non-reciprocity based on these systems. And now what we've been looking at are ways to manipulate in non-trivial ways entanglement in an asymmetric way by using the same devices. And for now, we're exploring mostly the theoretical implications of this, but as I said, in practice, it's not that we need to build different devices. It's more about the measurements and excitation of the system.
So you will be designing some separate entanglement circuit and then sending the waves. So
yeah, what we want to show is that you can get highly asymmetric responses to excitations from opposite sides, from non-symmetric, non-reciprocal structures like the one I showed you, based on nonlinearities. There can be quantum nonlinearities. So that's if you look at the advanced quantum technologies paper, I can send it to you a couple of months ago. We already speculated on some of these, but we are looking at the correlations, second order, third order correlations, and the features in terms of how the entanglement of coupled photons would be impacted by crossing these devices where there are no reciprocity.
So, you expect something in symplectic angular momentum bias, right?
Yeah.
Can you go back to that slide? Yeah. Okay, so it's like a magnetless circulator, right?
Sure. Yeah.
So, I mean, what will be the frequency response? Like, is that for narrowband or what will be the response?
Great question. So the original work, the one we introduced this, as you see from the references, from 2014, so several years ago. The original idea came from starting from a narrowband resonance that allows you to enhance, to slow down the waves as they interact with the ring, and then by applying this slow modulation, you can split the degeneracy. So instead of having a single resonance, you have two. Those will be inherently narrowband, and the quality factor of these two resonances, you see this schematically here, will be determined by the quality factor of the original resonance. In fact, the narrower that bandwidth is, the slower is the required modulation frequency. That is good when you want to keep the modulation frequency low, especially in optics. That's a good thing because you can do it with electro-optical modulation, for instance. Since then, we've done a lot of progress. In fact, I didn't have time, of course, to show you a lot of what happens behind it. But look at this response here. What you will notice of this structure, it's a bit more complicated structure, but basically it's the same idea. But essentially has a response that is frequency independent. This does not rely at all on a resonance. If you see the structure here, it has no inductors, right? So what we are doing in this structure is to replace the resonance with a second layer of it's like a parallel circulators, right, in the vertical dimension. And what you can prove is that time modulation can help you go around the need for a resonance. So here, this response essentially is quasi-static. There is just capacitors and switches. That makes the structure extremely compact, but also completely frequency independent, and can give you very, very large bandwidths. So that's possible. In fact, this paper is just impressed now, Nature Electronics. You can read some of these. We have also a couple of conference papers in which we explain why this can be so broadband. So the bandwidth is not an issue. I agree that in the first demonstrations we've shown, we always started from a resonance because we wanted to map what we did for sound into radio frequencies. But the beauty is that you do not need a resonance. So you do not need to make it a narrowband. For some application, the narrowband is good. In fact, interestingly, as we were talking to companies, the biggest interest came from companies that needed the narrowband. Because oftentimes, as you know, in conventional diplexers and wireless communication systems, you also need to select the channel that you want to use. So they liked that we got these narrow features on top of the non-reciprocity. But of course, for applications like true-time delay that I was showing, that's a bad thing. So that's not any longer a constraint that we have. The modulation frequency, footprint, and the bandwidth are not any longer a trade-off for these designs. And we're very excited about that. But it's a very good question. Yes.
I have a question about the slide that you talked about initially when you first started answering your questions, where you had the mathematical.
Yeah.
You talked about like how that could that tied to reconfigurable intelligent surfaces. Can you elaborate a little bit more on that? On the, it's not that slide. It's
the analog computing, you mean?
yeah.
Yeah. Yeah. No. What we have been working on in this problem is of course, most of what we've done so far is based on analog signal processing for images, image processing, edge detection, blurring we have done, or solving complex mathematical problems. But the beauty is that this same approach can be applied to arbitrarily linear operations for now. We are working on nonlinearities, but that's another story. So what we have been in discussions, in fact, we have a large NSF project on this with mostly people. We are the only kind of hardware people in this project. It's funded by this division. I never worked with this higher layer. But the other people are all in wireless communications. They work on reconfigurable intelligent surfaces. And one of the goals of this project is to essentially replace some of the digital processing of signals that can happen at the level of the reconfigurable intelligent surface into an analog response. So as your wave comes in, can we apply those operations as to the reflected beams? An example, we published already a paper on this. It's Doppler cloaking. What do we mean? One of the things we want to do, you can look it up, it's from last year. As users move in front of your reconfigurable intelligent surface, if they have a velocity that is orthogonal to the plane of the surface, there will be a Doppler shift. And this may be very small if the velocity is small, but maybe because we've been talking about these narrow channels, this narrow band operation, may be sufficient to actually detune the response. It's a problem that you may face. There are also other situations in which these Doppler shifts become very important for wireless communications. What we have shown is that you can build in into a surface a way to correct for that. So if you realize that one of the users is moving, you can actually embed an analog processing of the signals that when they reflect, they correct for the frequency shift and put it back in the right channel. That's one idea. But there are many others, right? In equalizing channels, there's a lot of operations that you do naturally in a wireless system. Now you can integrate it in the design of the surface. And the beauty is that compared to the designs I showed you so far, that are mostly in optics you don't have actually a lot of flexibility in modulating, in efficiently switching. In a reconfigurable intelligent surface, you have a lot more. You can integrate easily switches like the ones I was just showing, integrated devices, high nonlinearities. All of this is much, much better at radio frequency linear waves than in optics. So it's a very powerful platform, and we are very excited about the opportunities that come there. I can show you a lot more. I actually recently gave a talk on just focus on wireless communication systems, and I'm very excited about what we can do with it. Borrowing these concepts from photonics, bring them to kind of RF millimeter wave technologies.
Thank you.
Yes.
Yeah. In one study, you showed that to achieve the spectral control, you suggest like a non-local metasurface of the localized one.
Yeah.
So using non-radiating elements, etc. So what are the basic design considerations to keep in mind to realize such metasurface, non-local?
Yeah, excellent. So basically, our point is that there are two extremes. One extreme is the conventional local metasurfaces. So most of the work that we're used to, both in optical metasurfaces, which work in optics, or phase arrays, is to treat each element of the surface as an individual cell. And say, if I bring back the slide I had on this, basically we are used to think in these terms. Output at any given point is equal to input at any given point times the transfer function. And we can tailor that. We know how to do it. At single frequency, that's very powerful. In fact, unprecedented for optics. You can do 15 nanometer resolution of control. Much better than what we typically use in phase arrays, scaled with wavelength, of course. However, the price we pay is chromatic aberrations. As the frequency changes, these responses are very poor. The opposite extreme is a surface that has no spatial control. It's completely periodic. You cannot do anything else than just reflect. Specular reflection. But you can make it extremely delocalized. So you can make a spectral control very, very strong. The typical response, you may know, guided mode resonance. You have a very tight guided mode in a structure, extended. So this, of course, makes it completely delocalized. It's everywhere in space. But you couple it very weakly with the outside, with a small perturbation, like a grading, periodic structure. That will make it very, very selective in frequency, but there is no spectral control. What we argue is that you can combine the two. So you can create surfaces that at the same time has a very sweet control on the line width of the response, but by delocalizing. So of course, the tighter is the response, the more delocalized the modes are. But then you can pattern this delocalized mode. So a good example is the one I was showing you here. This one. So here, each of these elements has the same exact line width, the same exact resonance frequency, and that can be controlled, by the way, and the same exact polarization response. But each of them has a different phase. So then you can adiabatically tailor that phase and add wavefront control that here is beam steering. So you come in a normal instance, you get out at an arbitrary angle. That depends on how you vary this phase. But of course, this does not need to be linear gradient. It can be a length, like as I showed you before, can be an orbital angular momentum, completely non-periodic. So for the surface, there is this delocalized mode that comes from the fact that all of them have the same line width and the same resonance frequency, same polarization response. But at the same time, the phase can be controlled geometrically. So you can pattern any wavefront you want. And this combines both, the best of both worlds. So that's what we argue, that you can add to the conventional metasurface control on coherence, temporal and spatial, and on wavefront patterns. These are two knobs that are missing in the metasurface, like local metasurfaces, as we call them. We have a few papers, by the way, that have been published in the last couple of years. We have kind of a concept paper that is just coming up now in laser photonics reviews on this. Actually, if you look up the first author, Adam Oved with Alex Nosing, great guy, that is driving this from a theoretical side. In my group, we have a few experiments that will be coming up, demonstrating several of these concepts, actually, both for thermal and for kind of augmented reality applications. Yes.
Have you explored any of the metal to insulator transition materials for the metasurface?
Phase change materials. Actually, with Alex, we've done a few of these. It's very powerful. Of course, tunability is a very straightforward way of using it. There is always a trade-off with efficiency in these materials. One thing we've been very interested recently in looking at is the nonlinearities associated with these transitions. So that's something that we've been working also with DARPA in leveraging some of these for nonlinear applications. So there are these two. Now, tunability is a good one, and this is established, and applying some of these concepts to those materials gives you good tunability with the price of efficiency reduction. But the nonlinearities, it's another very interesting direction in that front.
So the light interaction method that you talked about, can that property be explored in the application of photonic crystal fibers, something like that? Because there we explored photonic band gap to allow certain frequency to pass by when block the other way. So can that metasurface be used there, or has the application?
Yeah, absolutely. That's a great question. We don't work in this area, but there have been. In fact, Harald Gissen, for instance, in Germany, is one that has been showing some metasurfaces to outcouple light in non-trivial ways from a photonic crystal fiber. And it is a great technology already established. We didn't look at applying this to that platform, but it's certainly powerful direction maybe for biomedical sensing. There are several or communications. Yeah.
All right then.
Thank you. Great
Thank you very
questions.
Everyone have something to eat. So if
Thank
no
you.
one is eating, but make sure you have